In this video, we will see dry run of the code.
Now let's see a quick dry run of this code. So we have this root node and we have k equals to 3. Okay. So let's see. We have this function called kth smallest function with root and k, and count will be 0. So let me define one count that is starting from 0. Then we have result. Okay. Result is null basically in the starting. Then this is not calling here. I'm calling this in order function, right? So let me first do a first call in order function with the root value of 5, right? So I have called in order function with 5. I'm denoting this with 5. Okay, I call this function. I will come here. Is my node is equals to null? No, it's not, right? So I will come here and I will call node dot left. Again, one function call node dot left. What is node dot left? This function. So I will call I with 3, right? And once I called it again, first I will execute this one. Is my node is equals to null? No, right? Again, I will come to here and again one function called node dot left. So again, I will call with I 2, right? Again, if node is equals to null, no, it's not, right? I will come here again and node dot left. What is node dot left? That is 1. So again, I will call one function, right? So again, I will call one function, right? So let me define this also. For 5, I have called 3. For 3, I have called 2. And for 2, I have called 1. Now I am executing 1. Is my node is equals to null? No, it's not. Again call node dot left. So again, I will call one function, right? That is I. And what is node dot left now? That is null, right? Here we have null. So I will call this null function here. Okay. Now, is your node is equals to null? Yes, that is null. So return. So now I will return from, right? So when I am returning from it, okay, when I am returning from it, can I say my I of node, this function is done? Yes, it is done, right? So I will return from it. And once I return from it, I will be here, right? That means this node dot left is done. What I will do, I will start my count. My count will be now 1. And I will check, is my count is equals to k? No, count is not equals to it. Then I will call in order node dot write. So what is node dot write here? So here I am at node 1, right? Node dot write is again null, right? So I will first call again with an value of null, right? Here with an value of null, right? But again, if node is equals to null, return. So I will return from it and I will return. So this will also simply remove from the step, right? So of my I1 function, right? What were the values? Calling left, right? Returning, then count. I have done the count, all these value, and then node dot right? So that means all the work of this I1 is done. Basically calling the left, I have done the calling, it got returned. Updating the count, I updated the count, and calling the right, yes, I called the right, it got returned. So yes, I1 is also done, right? So it will also return. So once it will return, right, can I say my I1 function is done? It's completed. Yes, it's completed. So once it is completed, I will come here and I will update the count. Count will be now 2. Okay. And I will check, is my count is equals to k? So count is not equals to k. I will come here and I will say in order node dot write. What is node dot write? Again null. So I will again call a null function, right? Not a null, basically a null value. And if node is equals to null, so I will return it. So I will return from it, right? So can I say my IN is also done? I returned from it, right? Once I return from it, I will come here. Basically this is written. So can I say my I2 is also done? I2 called I1, okay? It got returned and it called node dot write. It is also returned. So yes, I2 work is also done. Yes. So what I will do, I will return from it and I will update the count to 3. Not here, first of all. First of all, I will remove the I2 because I have returned from it, right? I have returned from it. And once I return it, I will come to here because this node dot left called it I2. Okay, I2 is returned. So I will update the count. Count will be now 3. And I will check, is my count is equals to k? So yes, your count is equals to k. Here k is equals to 3. I will store result node dot value. What is node dot value? That is 3, right? That is node 3 dot value. So I will simply store 3 and I will return from. right? So what I will do, I will simply return from it. So we call this thing, right? I3 called, right? This I2, and I will return from it. So that means I am returning from here, right? 3 to 5. So can I say my I3 work is also done? Yes, my I3 work is also done. So I will simply remove from, I will remove I3. So see one thing here. So you called this function, right? 3, then you are not calling the right one because we are having a return statement. So from I3, we are directly returning to the I5 that called. Okay, we are not calling 4 because for calling you need to come here and you are not coming here because you have a return state. So I simply return it. Now I5 is done, right? Basically I5, the work of I5 is calling node.left. So you called I3, you got a return value. Then again you will update the count. So count plus plus, you will count will be 4. You will check is your count is equals to k. No, it's not. So you will again call node.write. So I will call node.write. I guess if there is count is, we can add one more condition. If there is count that is greater than k, okay, then also return. That is also one possible. So you can simply remove some less iterations. So, but let's complete this one. So here I will call I6, right? So I will call first I6. Okay. Now from I6, is node is equals to null? No, it's not. Right. I will come here and I will call node dot left. What is node dot left? That is again a null value, right? So that's a null. So I will call node dot left with that is in. And is my node is equals to null? Yes, return from it. So I will simply return from it. Okay. Once I will return from it, okay, I will come here and I will say, basically I will come here, I will update the count. Count will be 5. Is count is equals to okay? No, it's not. Then node dot write, I will call again node dot write with a null value. Basically here we have also null value, right? So this in was done, right? Completed. Okay. Then we have updated the count and next in is called that with the null value. That is also done, right? Because null will simply return it. When node is equals to null, it will return. So it will return from it. Okay. Can I say my I6 work is done? Basically it called the left value is returned. It updated the count is updated. It called the node dot write. That is also done. So can I say my 6 function call is also done? So yes, it will get removed. Okay. And it will return back. Now I5 is also done. I5, the work was I5 call node dot left, updating the count, node dot right. All the 3 works is done, right? So yes, I5 is also done. So what I will do, I will simply come out from the recursion stack, right? And I will come from here and in the last, I will return the result. What is stored in the result? The stored value is 3. So I will print 3. And that's why the answer will be 3. Okay. So what will the time and space complexity again here? The time complexity will be because of n, because of traversing the all nodes, and the space complexity will be because of height of the binary tree because see, this was the longest path that you have traveled, right? The longest path. So you can see the recursion stack. There were different function calling one by one. Basically, height of your binary tree will be the space complexity. So yeah, that's all for this problem. Okay, this was a good problem. Kth smallest element in a binary search tree. I hope like now the trees concepts is clear. We have solved, I guess, more than 6-7 problems here in the binary search trees. Okay, but let's see if you want more. I want to discuss few more questions that are more important, like that are on the harder ones. Okay, so in the next video, you can check out more problems on binary search tree. Okay. So yeah, go ahead, check the next video. That is again one problem on the binary trees.